All right, in this video, we are going to use this function and determine where it is increasing, decreasing, and where it has its maximum and minimum values. So, first things first, first thing that we want to check is the domain of the function, even though it didn't ask for that. First things first, think about the domain. All right, so this is a polynomial function, right? So basic polynomial function, we might have different exponents or whatever, but whole number exponents, and it's just a sum of terms with different degree polynomials, and constants, maybe constant terms. So every polynomial function has the same domain, and nicely enough, it is all real numbers. So I'm going to write that in interval notation here, but you could write that using some sort of other notation. So particularly in functions where the domain might be restricted, that will be important in some of our later steps. But it is helpful here to make sure that we think about the domain of the function. All right, so first thing, that's always what you should do, even if it doesn't ask you that. And then when we're doing a problem like this, we're really using the derivative. The derivative tells us about slope. And so the first derivative tells us where the function's increasing and decreasing. Remember, where the function's increasing would be where it has a positive slope, so a positive derivative. Where it's decreasing would be where it has a negative slope, going downhill. And then the maximum and minimum values are going to occur where it changes from increasing to decreasing or vice versa. So we're going to find those things by, first of all, finding the derivative. And so we're going to find the derivative. And we're going to look at where the derivative is not positive or not negative. So we're going to look at where the derivative is 0 or does not exist. Those are called finding the critical values. So that's important vocabulary, that if it asks you somewhere in here to find the critical values, you know what it's talking about. So the critical values are sometimes called critical numbers of the function. That would be the places where the derivative is 0 or does not exist, but values that are in the domain of the function. So I'm going to find the derivative. This one's a pretty straightforward derivative. We're just going to use power rule here. And then minus 12x to the first, so minus 12x, and then the derivative of that constant term will be 0. So there's our derivative. And then we want to think about where this derivative is 0 and where it does not exist. So I'm going to start with the derivative equal to 0. Right, so I'm just going to put in 0 for the derivative and then solve for x. Okay, so this is where all your prior algebra skills come in, and we've been practicing, reviewing some algebra kind of as we go. But in this case, when I have an equation equal to 0, one of your best strategies is going to be to factor, if you can. So all kinds of different factoring strategies here. I would notice that I have some common factors in each term. Each of these terms contains a 3. 3 goes into 12 4 times, and it contains an x. So I'm going to, on this one, start by factoring out that common factor of 3x. And then when I factor 3x out of this term, I'll be left with an x. And then in this last term, I'll be left with a 4. And I've got the minus in the middle here. Okay, so if you have an equation equal to 0 and you can factor, why that helps is that you can then set each factor equal to 0. The only way a product of two things is equal to 0 is if one or the other of those things you're multiplying by is 0. So that tells us that either 3x is equal to 0 or x minus 4 is equal to 0. So setting those two factors equal to 0. And then I have simpler equations that I can solve for x. So on this one, I will just divide by 3 on both sides. And so I'll get x equals 0. That's one of the critical numbers. And then the other one here, I'll just add 4 to both sides. So x equals 4, the other critical number. All right, so I have two critical numbers from where the derivative is 0. They are only critical numbers if when I set the derivative equal to 0 and solve for them, they are in the domain. So the domain is all real numbers, so these are. So these are our two critical numbers, critical values, perhaps. Different texts call them different things. The other thing that we should check when we find critical values is where the derivative does not exist. So under thinking about critical values, you really have two things to think about. This students tend to remember setting the derivative equal to 0 and solving for x. the other part students tend to forget, and the reason is because a lot of problems, this doesn't happen. And this is a problem where that doesn't happen. So you need to think about that though, because there are a few problems where the derivative does not exist, and you need to think about that. Okay, so the derivative is equal to 0, solved for that. Derivative does not exist. So I'm looking at this derivative function and thinking, are there any values of x for which this function does not exist, this derivative function does not exist or are undefined? And there are not. If you had things like denominators, that could be 0, or roots that might involve things with restrictions on your variables, then maybe there would be some values where the derivative does not exist, but not on this problem. This problem, the derivative exists for all real numbers. Okay, so I don't get any critical numbers from that part of the problem. Students tend to forget that, but we will look at some examples where you do have that issue. So 2 critical values. So 3 main steps in problems like this. First things first, always think about the domain. Second, find those critical values. All right, and then the next thing that you're going to do is make a sign chart to analyze what the derivative is doing around these critical values. And so this looks different when you look at different examples. Different people might organize this work a little bit differently, but I'm going to do it one way and then talk about some other ways to do that. So we're going to make a sign chart. All right, so what the sign chart is essentially a number line. And on the number line, you're going to put your critical values and also any endpoints of the domain. This domain doesn't have endpoints since it goes from -infinity to infinity, but some problems do. So in this case, we just have the critical numbers. So think about in a number line where the numbers would be, which one is left of the other one. You don't have to scale off everything on the number line, but you do want to think about that x equals 0 is left of x equals 4. Right, so I've labeled those critical values on the number line. Those critical values and any endpoints of the domain split that number line. Sometimes I call those split points. They split the number line, the domain, into different regions, in this case 3 regions. So those values split the number line. And then what I want to do is test between these two, left of 0 and right of x equals 4, I want to test to see the signs of what? That's what sometimes students are confused about. So if you just go back and think about what we're asking about, we're looking at where the function is increasing and where the function is decreasing. And one of the things I said at the beginning is that when the slope, which is a derivative, is positive, then you have a function that's increasing, going uphill. And the function's decreasing when you have a slope, which is the derivative, is negative. So this is what I want to check the signs of. If you get confused about what you're checking the signs of, is it the original function or the derivative or something else, just go back and think about what it's asking you about. Right? We're thinking about increasing and decreasing, which is when we have a positive or negative slope. So we need to check the signs on that first derivative. So I'm checking the first derivative. All right, so I'm going to test numbers left of x equals 0, something between x equals 0 and x equals 4, and then something to the right of x equals 4. And I'm going to test those values in that derivative to determine, I don't really care about the numerical answer I get, but just the sign of that first derivative. So I can use this form, or I actually here am going to use the factored version. Some place down here I factored out a 3x. It's maybe a little bit easier to check the signs in that factored version. So I'm just recopying that same factored form that we used before. I'm going to check by plugging numbers into this factored version of the first derivative. All right, so I'm going to start by plugging in a number that is left of x equals 0, like x equals -1. And you can actually plug in x equals -1 if you want, but I really don't care about the numerical value of that. I really just care about whether the answer is positive or negative. So I'm just going to think about it, and this is when the factored form is helpful. If I put in 3 times -1, I'll have a -3. And then when I have a -1 minus 4, this will be -5. So I'll have a negative times a negative, which is a positive. So I'm going to label here f prime of x is positive. In some of the online homework, they write this a little bit differently, but I usually, when I write these, just write pluses and minuses. I left some space down here for how I might label that, and some of the online homework does. So I'm checking. I just plugged in a number, left of x equals 0. You don't necessarily need to write something down for that. You can do that in your head. And what you're checking is that derivative positive or negative. And then same thing in between here, between x equals 0 and x equals 4. I'm going to pick something in there like x equals 1 or whatever. And again, I don't care so much about the number for the answer here. I just care about whether the answer is positive or negative for the derivative. So when I put in x equals 1, I'll have 3 times 1 is 3, positive. And then 1 minus 4 is negative 3, so I'll have a positive times a negative. Positive times a negative is a negative. And then when I plug in a number bigger than x equals 4, like 5 or 10 or whatever, just anything bigger than x equals 4, again, I'm just plugging it into these factored form. So like 5, 3 times 5 will be 15, so positive. 5 minus 4 is 1, positive. So positive times positive is positive. Okay, so I've made a sign chart where I've checked signs of the first derivative. But then I want to use that to help me answer what it's asking here. So remembering that if the first derivative is positive, that tells us that the original function, f, is going to be increasing. And so you can write that increasing in this region of x values. But I sometimes like to draw an arrow just to remind myself visually what does it look like when I have a function that's increasing. It's going uphill. And then when the first derivative is negative, our function, the original function f, will be decreasing, so downhill. And then again, when the first derivative is positive, the original function will be increasing. Remember, derivative is slope. Positive slope is going to be going uphill, increasing. And so that looks like this, right, going uphill. All right, so these little pictures that I drew with these arrows, our online homework doesn't do those, but I find them really helpful in sort of thinking about what the graph looks like and whether these points give us maximum or minimum values of the function. All right, so at this point, I actually have done all of the work that I need to do, and I can go ahead and write down answers to my question that was asked here. All right, so we were asked to determine where the function is increasing. So this region where x is left of x equals 0, the first derivative is positive, that's where the function is increasing. So I'm going to just write that how you might see that written either in a written answer or if you're filling in boxes in online homework. We might say that the function f is increasing on, and then this is an interval of x values for which the function is increasing. So in this case, I'm where x is left of 0, so x less than 0. So that interval would be negative infinity to 0, left of x equals 0. And then it's also increasing over here when x is right of 4. So you can just put a comma. I'm OK with that in your writing. In the online homework, they usually want a union symbol. So either of those would be OK. Union, and then 4 to infinity. OK, so those two intervals, when x is in those intervals, these are intervals of x values from my sign chart here. The function is decreasing on this open interval between 0 and 4. And then, especially if you've drawn these little arrows, it's maybe easy to think about maximum and minimum values. Remember that a maximum value would be a high point on a graph. A minimum value would be a low point on the graph. So if the graph is going up and then down and then up again, these little arrows can help you identify that this is going to be the location of a maximum, and then this one is going to be the location of a minimum. It'll be a valley when you go down and then back up again. All right, so we have a maximum. I'm going to talk about what kind of maximum that is and there are different ways that you might give this answer depending on how the question is asked or what on the online homework, what they've asked you to fill in the blanks. I'm going to go ahead and give this as a point. And so because these with parentheses sort of look like a 0.04, but that's really an interval, I'm going to label that this is a point xy equals, right? So the x coordinate of the point where we say that it has a maximum is at x equals 0. And then I'm going to fill in here in a minute what that y coordinate is. And then we have a minimum at another point. Our online homework has like this. It'll say a minimum at xy equal, the point xy equals, and then you have to type in the blanks. So our minimum is at x equals 4. Okay, and then this is another place where sometimes students get lost in the problem and they're not sure where to get the y coordinate of that point. But just thinking back to algebra class a long time ago when you first plugged in numbers, inputs and outputs, those were not in your derivative because you didn't know about derivatives yet. So xy points, inputs and outputs, those come from the original function. So in order to find these input-output values, I'm just going to plug those numbers into the original function. You could plot a bunch of points on the original function, but in algebra, maybe you made xy charts, or you can let your calculator do some of this work. But you're just putting in the x coordinate 0 and the y coordinate 4. I'm going to figure out the y coordinate by just plugging in those numbers to my function. You didn't know about derivatives when you made these xy charts before, so you're not plugging into the derivative to get these y values, right? Plugging into the original function. So when I put in x equals 0, that all will be 0, and I'll get y equals 1. And then I'll put in x equals 4, and then you either have to work this out or think it through, right? So 4 cubed is 64, and then 6 times 4 squared will be 6 times 16, so 96. So 64 minus 96 will be negative 32 plus 1, so negative 31. All right, so that is our maximum value here is at 1, 0, 1, and the minimum value is at 4, negative 31. All right, we will do some more with second derivative and kind of putting it all together to sketch the curve in the next unit that we do. But you could get out a graphing calculator if you have access to that, or if you're on a test where it's restricted that you don't have a calculator, you would just have to have faith that you've done this work correctly so far. But you've got kind of a rough sketch of what that function looks like. You know there's a point at 0, 1. You know there's a point at 4, and then way down here at negative 31, my scale's going to be off here, but 4, negative 31. And I know that the function is going to be increasing and then hit a high point, and decreasing and hit a low point, and then increasing again. So you can get a kind of rough sketch of what the function looks like without necessarily even needing a calculator to help you. If you did graph it on a calculator, this would probably be off your viewing window anyway, so you would have to know it's there to go down there and find it. But we'll do some more with second derivative in a later video and talk about how to get an even more complete understanding of what this function looks like and acts like.